Hi, I'm Jadi and hope you are doing well. You are watching Geeking with Jadi. Sometimes I read source code, sometimes we hack things, and other stuff. In this case, there was a huge news yesterday. OpenSSH had a serious security problem. Far from OpenBSD guys. OpenBSD is known as one of the safest operating systems in the whole world. OpenSSH comes from them, and now they have a security problem. Fun fact, OpenBSD is much more safe compared to other systems, even in this specific hack, because things like its ASLR and other stuff, which I will cover. I will try to show you technically what had happened, show you the history, some source code, and give you a better understanding of the whole thing. This is super technical. I also do not understand it in depth, every single thing. I cannot rewrite anything close to this, but I kind of understand, and I can show you where you can learn more. Let's see. So they said we have a security problem related to a race condition in SSHD. What is race condition? Race condition is in computer science. It's about the when two threads or two different things working and they have a race. Sometimes this may finish faster, sometimes this. Very simple case. You have a program which has an x is 5. You have a thread which wants to multiply the x into 2. One wants to add 1 to 2. You start both threads. What is the result? You don't know. This is a race condition. If this goes faster, so it multiplies in 2, it will be 10, and then this finishes and the answer will be 11. In another case, maybe this goes faster, this finishes first, so your x is 6, then this finishes, multiply it in 2, and it will be 12. This is a race condition. You can run this many times and see different results. In more technical cases, you want to read a variable from memory, do something with it, write it back. Someone else is doing the same thing, and there is no lock. So maybe you read it first, return back, then this reads. Maybe both of you read the same thing. You write faster, then this overwrite you, and these kind of stuff. These are called race conditions. And there is a very known attack on the race condition, especially when you are using glibc, which many Linux and Unix distros use. This is well known from the years 2000s. We will see. So there was a problem with the race condition. Now it is solved, only shown on 32-bit Linux with glibc, but it's known that should be possible to do the same thing on 64 bits and non-glibc systems. It says under lab conditions, the attack requires on average 6 to 8 hours on connections up to maximum the server will accept. So it's not like that someone just got root access to your server with one click or one connection. They need 6 to 8 hours. If you have not updated your system, update your systems before watching this video, then return back. Now subscribe, tell your friends, and then return back and update and do everything. Whatever. So they say we thank the Qualys Security Advisory for reporting this. Just do a search for Qualys Security Advisory. I will add the links to the show notes, descriptions, whatever it is called. It's a very descriptive case. Qualys Security Advisory, they say, very nice. Computer geeks, regression in SSH, RCE, remote code execution in OpenSSH servers with glibc-based Linux systems. CVE 2024 6387 if you wanted to search. First they gave the summary. They said what they found, how they started. There was same problem in OpenSSH before version 4. Then it was fixed, but it seems on version 8.5, someone mistakenly removed this if-def. Strange thing happening, especially after Y attack we had. So they said this is a remotely glibc-based Linux's exploitable, and it's related to malloc and free. Let's get a little bit more technical. They will show 3 different attacks on 3 different parts of the OpenSSH, same logic. I will go through only one of them to show you how it works. The main logic behind it is there is a very, very nice article. Read it. It's old, maybe 2000, 2001. It's delivering signals for fun and profit. Search for this and read it. You may want to go very deep, understand more than what I understand. Everything is there. You can go deep, or maybe you just want to watch and have a general understanding based on what I try to show you. The general idea is a race condition about free on glibc and malloc on C programming. When you want some memory, you want to do something, you create a pointer. You say my pointer 1 needs 1 megabyte of memory, so I want to save something in the memory. So you say malloc, I don't know, 10 bytes to my memory. It returns back part of the memory which is free to your pointer. Malloc does this. So you call malloc 10 and get 10 bytes of memory, put it on your pointer 1. Later you can free this. When you have done with this, you have to say free my pointer 1, and this will free the memory. But if you have 2 different ones, a race condition may arise. Search for delivering signals for fun and profit, and it will show you a very, very common attack. In many cases and in many programs, when programmers want to handle signals are signals you send to your program. So for example, when you push that red button to close your window, it's a close signal. When you kill a program, it's a graceful kill signal. When you kill with -9, it's a very aggressive kill signal. These are different signals. There's another signal, for example, for SIG alarm, which sends an alarm that time is finished, timer is done, whatever, to your program. It's a very common practice to have a signal handler in your program. You say, okay, do a syslog, write into the system log that I'm closing myself because I've got a signal with this information. Free your pointer, free your other pointer, do something, blah, 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 and exit the program. This is a signal handler. This is a very common signal handler you see in many programs. Later, you might have this. Okay, if you got hop signal, call this. If you got termination signal, call this. And then you create 2 different pointers. The problem starts when you call this twice. Normally, if you call your signal handler once, okay, this will work. You will write here to the logs. For this, you need some memory allocation. You allocate something in the memory. Then you write it in the system logs. Then you free your pointers. Then you exit. Normal. If I call sig, for example, hop to close this, this will happen. If while this is being running, you run another sig hop, you send another sig hop, it won't go through because one sig hop is working. But you are using this for 2 different signals. So if you send a sig hop to this program, it starts to run. Meanwhile, when you are in the middle, you send another, for example, SIG term. Same thing will start running. And here you may have a race condition. If you follow this great article, Delivering Signals for Fun and Profit, there are some code samples. It will show you how you can break things with this. This is a sample. It says, okay, log to the syslog, free your pointer, free the other pointer, sleep for 10 seconds, then exit. And you are doing this. If you cut it like this and say, okay, log this, that, and sleep one, then send hop, you will see the problems. You are sending two different signals to the same program, and you will see the corrupted heap. If you want to understand deeply, search for Delivering Signals for Fun and Profit and read it. This is not our story. The Qualys Security Advisory people started to study the OpenSSH's source code. Practically, they were searching for two different free calls in a signal processing. So if they can call this twice, they may have this race condition. I will go deeper. When studying the source code, they found out that in OpenSSH, the grace alarm handler handles the alarm signal. Okay, you've got that time is done, my alarm is ringing, my SIG alarm is here, time is ringing, so normally you have to close your connection. This function calls packet close. They went and checked the packet close. Packet close, because you want to close your connection, so you need to close your packets. It calls buffer free on input, buffer free on output, buffer free on outgoing packets, and buffer free on ingoing packets. So you are closing input, output, packet input, and packet output. What does buffer free do? Buffer free mem sets something and then calls xFree on this buffer. What does xFree do? It says if the pointer is null, give an error, otherwise call free on this point. So if you send a alarm signal to Grace alarm handler, this will be called, so you are calling this and hence this 4 times. You found what you were looking for. You know about this attack. So they were very happy. They started with a very old version of Debian because it's easier to find exploits there. Later they will go for newer versions. So they found out that if they send a SIG alarm, free is called 4 times. This is cool. So they have a way to call free 4 times. But what happens when free is being called? That version of Debian is using glibc, as many other operating systems. So in glibc, when you want to clean your memory, you have something like a malloc chunk. This is the struct. So when you have your heap, you have your memory chunks here. Each of them have this structure. Previous size. So if you are here, you have the first number. The previous size is shown. Then you have your own size. Then you have your forward and backward. FD and BK is very well known. Then you have your data here. This is a linked list structure, double linked list. So each of the chunks know the previous size, know its own size, know the forward link, and know the backward. So you have links to both sides. This is a double linked list structure used for the heap. If you want to do an unlink, what should you do? You have an unlink function here. It says if you want to unlink this, so delete this, first you set a bit and say this is not used. But let's talk about it later. If you want to delete this, you do. Back will be your P to the back, this one. Your forward will be P to the forward, this one. So it's enough to say forwards. So these ones, back, should point to your back. And back ones, so these ones, forward, should link to this one. So you are deleted. You just find your back and forward, point them to each other, so you are not used anymore. This is how linked lists work. Hopefully you should know it. It might be a little bit confusing. You can go deeper, read this 3 times. I read this 2 times to understand how it works, and I knew about the attack. I knew about different things. So take your time, and this is a way to learn new things. So we have malloc chunk. This was the chunks I showed you. We have the unlink. Now, when we want to free our memory, so when we want to call the free, what we do? We create a header field, previous size, then we calculate the size, we have the next size, and then we say if in use bit at offset next, if next is not used, unlink it. Otherwise, set it as unused. So clear in use, set it as unused. Then do those linking things I showed you. So when you want to free a memory, you set the in use bit to 0, say it is not used, then do that linking, unlink, and you are clear. Here is very important. To exploit this code path, you are sending some data to the heap, right? You are talking with OpenSSH. So you create this structure in the memory because you are writing this data, you are talking, and you are sending some chunks of data. You send chunk X, chunk Y, and chunk Z. You know how the heap looks like. Then you call free on this. Let me scroll a little bit to show you all the code. You call free on this one. Okay, what happens? It goes through this logic. You're sending a SIG alarm. So practically you start with a SIG alarm. You send SIG alarm. So the system wants to call free. It calls free on this. And going through all of these code. This is not in use. So the in use will be set here as 0. So the heap knows that this is not used. Then it wants to do this. But assume that when you are here, in use is unsets, clear in use bit. This has not happened yet. You sent another SIG alarm. So this is fun. In this case, this runs on X. If you can synchronize your timing, it's very difficult and there is no way to do it. You have to do it times and times and times and times and hope, and if you believe, pray for one chance that your Y, or as you say in Western world, Y is here. Sorry, let me undo this. So you have to hope that your Y free is here and your X free reaches here and unlinks this. In this case, this has not happened yet. These pointers are not valid anymore because you have unlinked this. Once more, you are praying to have your SIG alarm on Y to be here when your chunk X reaches here SIG alarm. So you're sending 2 SIG alarms, one for this, hope for this situation. In that specific case, you can have this user data written here, and there is a well-known attack which is called almost arbitrary 4-byte mirrored copy, overwrite, sorry. This is described in a very nice article. It's here, frac.org. Frac used to be the best ever, and still I think it's the best ever publication you can read online, freaking and hacking, and it goes back to 20 years ago, but still many things are valid, including this one. Search for frac, issue 0x, so it's in hex 3D. And the article we are looking for is advanced Dogley malloc exploits. It tells you how you can exploit this race condition with writing 4 bytes when this happens. It's a very, very long read, and you have to read it times and times and try to understand it part by part. But at the end, it lets you to write 4 bytes, kind of any 4 bytes, kind of anywhere you want. So when you have this race condition and you are controlling this part of the data, you can, and you have that specific condition I've told you, you can write 4 bytes anywhere you want. Now the attack is easy. I've told you, the logic is easy. If that condition happens, you can write the bytes you want anywhere you want. Now you can write a shell, a remote shell somewhere, and write a jump to your free hook. So whenever glibc does a free, this hook is called. You were able to write your data anywhere you wanted. So you write your data somewhere, you write the address in this hook, and as soon as free happens, your shell runs. And OpenSSH runs with root access. So you have a root shell. The first time this team tried to do this, it took them a month to reach that specific condition. But that was a proof of concept that they can do this. Then they went to make it faster and faster. They started on Debian with a very old version, because that version didn't have this ASLR, which is address space layout randomization. In the modern system, we have this on OpenBSD. This is very aggressive. Even when each time you are booting, your kernel is different. But this randomization of memory makes it very difficult to write your bytes in a correct place and then jump to it. Also, this NX is a possibility on the CPUs, which is non-execute. So you say this part of memory is not executable. So even if you write your shell here, CPU won't execute there. It makes everything more difficult. So they went for a 32-bit system with an old glibc, without ASLR, and also without NX. So it was a proof of concept. Still, it took them a month to execute it. But later, they started making it faster. If you read the article, search for it. It was Qualys Security Advisory, RCE in OpenSSH. They don't have the proof of concept code, but they have enough things if you want to learn, not produce. If you want to produce, you can start from delivering signals for fun and profit and learn from that one. They have a very, very good code which you can execute on old glibc. Anyway, one way is to install a very old version of Debian, so you can have this. They started from what I've told you. It was very slow. They started to practice it on the main thing. They started from the DSA public key encryption because it was calling X-free. They were not successful. Then they found out that key from blob has 4 calls to free. So they can run this 6 times, so they have 24 frees in each try, and this can be much faster. Still, it was about 1 month. Then they started finding different ways. For example, sending DSA data, but not sending the last byte. So it took longer. Server was up. They were able to abuse it with more alarms, most probably, not sure. So they made it faster and faster and went for the second phases in different parts of the code, which was able to run on Ubuntu 6.6. And then on the PAM, they did the same thing. They were searching for places which were faster and easier to execute. And then they went for another part of the code, which was running, I believe, on a newer one. Yes, they were able to go for Debian 12, so the latest one, and executed this, and this also worked. Then they said we switched to 64 bits because it's more common, but we saw a bug reported to OpenSSH, and we believe that this is the same case. So we contacted OpenSSH people with our configuration and with our exploit and showed them how this can be done and everything. So it's a very nice read. You have the general idea how this happened. And again, I've told you, if you really want to go deeper, search for this delivering signals for fun and profit, and also read this great article in frag number 3D to see how this AA4BMO hack happens. You can write 4 bytes wherever you want when you have an exploited heap. And then they finish with how to mitigate this, which is for most of us just updating it, but you can also do, this is not the case. This was what I was looking for. Sorry. On timing, they show how they can do it faster. For mitigation and patches, you can update your OpenSSH. If you have not done it, do it quickly. But they have other methods too. For example, reducing the grace timing to 0, which has some other problems, but would work for this one. Or SSH SIG ID, you can just disable this part, not to lock it, so they cannot write to the memory whatever they want to make this attack possible. Because this is calling the syslog v. There is another version of syslog v-r, I think, which understands this async thing, and you cannot do such an attack using it. OpenBSD uses it. Love OpenBSD. Anyway, sorry if this was a little bit confusing, but this should be a fun watch or a method to start your own journey. Start from delivering signals for fun and profit. And you don't need to understand 100%. Trying is learning. Have fun. And tell your friends and subscribe and do whatever people does. That makes me happy if you enjoyed this.